Welcome to the next lecture in our SIS2 networking video series, where we're going to look at the application layer. So we're going to look at our protocol stack. However, before we get started, let's have a review of what we've looked at so far. So in the first lecture, we introduced the basic concepts of how we communicate across our networks, how it can be organized in terms of circuit switching and packet switching. I'm not really going to go any deeper into communication theory, so as long as you've got a basic understanding of the difference between circuit switching and packet switching, that's good enough for this module. Our main focus is going to be looking at the different protocols we're using across our network. So we're going to look at the internet protocol stack and see what protocols are used at different levels within a network. So what types of protocols do we need to route our packet across the world, across the internet? That is a wide area network, or WAN. And what protocols do we need when we're transferring packets across a building on our local network, a LAN? And we'll see those as we pass down our protocol stack. From a teaching point of view, a protocol stack is quite nice because obviously when you're looking at a particular protocol at a specific layer in our protocol stack, you can ignore all the underlying protocols. It just all magically happens. So we're going to start at the top at the application layer. And in this lecture, we're going to look at HTTP, SMTP and FTP. So the protocols used to transfer your web pages, your emails, and your files. We'll also be looking at other application layer protocols in the next set of lectures. So we'll be looking at the more housekeeping side of things. So the DNS, DHCP, and NTP. So the protocols that are used to resolve your names. So your domain name into an address, the protocols that assign each machine a network address, and a protocol that tells you what time it is. Okay, before we get started, a quick quiz to see if you understand the joys of packet switching. So we have this network scenario to analyze. So we have multiple hosts that want to communicate across this network to different servers. And this connection, this network, is made up of multiple channels, multiple communication links. So each host here is connected to the first switch in our packet switch network by a 40 megabits per second link. This switch then is connected to another switch across a 100 megabits per second link. And then finally, your data is transferred across a 20 megabits per second link to a particular server. So the question is, how long will it take to transfer a 1 kilobyte packet from one machine across this network to a server? And obviously to work out that delay, you can start to approximate it using this equation. However, we need to start to think about the worst case scenario. So are there any other factors that could affect the speed that we can transfer these packets? So again, think back, what is the difference between circuit switching and packet switching? What does circuit switching give you that packet switching does not? So where are the bottlenecks in this network? As it says at the bottom there, a few hints. So do think about bits, bytes, and storing and forwarding. Remember, just the same as our letter analogy that we had in the previous lecture, where we're using the postal service to send a letter to somewhere in the world. Same thing here. Think about how those 1 kilobyte packets are stored and then forwarded across this network. So we have a 1K packet that will be transferred and stored in this switch. It will then be transferred across to the other switch before it's finally transferred to the server. So what problems could occur owing to the nature of our packet switch network? That store and forwarding technique. As always, we will be looking at the answer in the lecture review session. As I said at the beginning, this module is organised around the analysis of different protocols used at different layers in our protocol stack. However, just to make things confusing, there isn't just one model of a protocol stack. There are 3 commonly used. The OSI, so the Open Standard Interconnect model, that has 7 layers describing how you should organise your protocols and design your networks. We have the Internet Protocol Stack, which is a 5-layer model, and that's the one we'll actually be using. And we have our TCP/IP model, which is just a 4-layer model. So the intention of all these models is to break down that communication problem into identified functions. So as always, when you do design, each layer should do one thing, and it should do that one thing well. So that separation of design concerns, ensuring that data is not replicated in multiple layers. And later on, we'll see how we can do that using encapsulation by adding headers as we go down this protocol stack. So the question arises, why did I choose the 5-layer model rather than the 4 or the 7? Well, I think it reflects the different protocols we'll be looking at in a little bit more detail. So yes, the application layer in our internet model does group together 3 layers from the OSI model, so session and presentation, so how you start and end connections, how you do encryption, those sort of things. That's all within there still, but we're not looking at that one in so much detail in this module. So breaking it down into this final level detail is perhaps a bit lost for this module. So that's why I chose this model in preference to the others. So it gives you a nice balance of abstracting away from some of the detail, but including some of the detail is lost in the TCP/IP model. And as always, you could argue I've made the wrong one, but that's what I'm going for. Okay, to break that down a little bit more detail, so let's fill in those blanks. So what is the application transport network link and physical layers? So layer 5, your application layer, don't get confused. That's not where your applications live, so like your web browser or your mail client. At this layer, we're providing the API to the network. So something your web browser can connect to. So at this layer, our unit of data is called a message. So we'll be transferring messages, typically between clients and servers. So the first examples of that we'll be looking at are HTTP and FTP. So your hypertext transfer protocol and your file transfer protocol. So for example, your web browser may want to request a HTML object from your web server, so an image or some text. And that would be sent as a message to that server. So the get command, give me some data. And we'll see an example of that one. We'll capture some Wireshark packets of that actually happening. Actually, it's quite surprising how many protocols live in this application layer. You may think of it kind of an application as those kind of user-centric clients, but you've also got a number of housekeeping protocols in there. So for example, when we access our web page, we'll use typically a URL. So we'll have a domain name that we need to convert from a human-readable form, www.google.com, for example, into a network address, an IP address. And that's done by your domain name system, so your DNS server. Equally, you need to connect to the network. So to connect to the network, you need a network address, an IP address, and that's given to you using your dynamic host configuration protocol, or DHCP. As I say, it's surprising how many protocols live in this layer. Some of the protocols like routing protocols, you might think, ooh, routing protocol, that will be a low-level protocol. But no, RIP, OSPF, and BGP all live in this layer because they want to talk to other networked devices. They want to communicate across the network. So to do that, they need to make use of the transport layer, our next layer down our stack. So this layer breaks down your message down into segments, smaller chunks, and those are communicated across that network. And do that in different ways. You can do that using reliable or unreliable communication protocols. So a reliable communication protocol is TCP. So TCP, or Transmission Control Protocol, ensures that when you send a segment, it's received the other end and it's received in the right order, and all is good. But obviously that comes at a cost. All of that fault tolerance and reliability functionality in this protocol comes with an overhead, a processing overhead. So if you're not overly concerned if the data gets there or not, because perhaps you can ask for it again later on, then UDP may be the protocol to use. User datagram protocol. That's a lot simpler, and so it's a lot faster. So it gets rid of the error detection, flow control, congestion control that we'll see later on when we look at these protocols. Okay, moving down the layer again, layer 3, our network layer. So just to confuse you, our unit of data, this one is called a datagram, and the protocol we'll be looking at is IP. Obviously, there's different protocols you could use, but IP is obviously the dominant protocol, and that's the one we'll be looking at. So here we're more concerned about how do we route our packets, our datagram across the network of networks that is the internet. So how does our data find its way across that packet switch network? And we'll see how it does that one using IP. Layer 2, we're now starting to think about how we move data around on our local network or a local area network, our LAN. And typically we do that with Ethernet, so Ethernet frames. So a slightly different problem to overcome. For this one here, we know all our hosts are on the same network. So how do we communicate on that local area network? And as always, we have a suite of protocols at this layer to allow us to do that one. So we'll be looking at our Ethernet protocol. We'll be looking at how it identifies hosts on the network using MAC addresses rather than IP addresses. How we resolve between the two, so our address resolution protocol, so how do we map between an IP address to a MAC address. So a lot of information there, but we will be looking at in more detail as we go through the various lectures and labs. Finally, we get down to our physical layer, layer 1. So here we're looking at how the actual data is represented on the wire. And what wires are we using? So are we using copper wires? So using twisted pair, Cat5 cable, Cat6, Cat8. So all these cables look remarkably the same, but they all have subtleties that allow them to communicate at different speeds. So the amount of shielding they contain, for example. Alternatively, obviously you could look at fibre optic cables. So we're looking at how we communicate the data as pulses of light now, rather than electrical signals down the wires. At this layer here, we don't have our software protocols because obviously we're dealing with the hardware, but we have obviously standards that define what voltages and speeds, etc., what connectors and sockets we should use to connect our machines to the network. So again, just to reinforce that one, at the application layer, we are dealing with messages. Those are broken down into segments that are carried by datagrams and frames across our network. So at each layer, we need different information so the network knows what to do with that packet. So what we do as we go down the protocol stack from the application layer to squidging it out onto the actual physical wire, we add headers, we add information to the message that allows the network to move that packet to the next stage, allows the network to communicate this data across the network. So as you can see, as we go down the stack, our packet grows. We start off with a message, then we'll put on our transport headers, some TCP headers, for example. Then this segment is then passed down to the network layer, and then we put on our IP headers, the information we need to route the protocol across our network, our wide area network, our WAN. And again, that packet is passed down. It's added another header. You add your Ethernet frame header, detailing the source and destination MAC addresses, for example. So each layer adding additional information to our packet that allows it to be transported across the network. And obviously, when we receive a packet, it'll go the other way. So when we receive our Ethernet frame, is it for us? So we look at the various headers and go, yeah, that's for me. So you pass up to the next layer up. At this layer, we'll look at the IP header and go, do we need to forward this packet on to somebody else? Or should this packet be dropped? Eventually, you'll get to a machine. So it'll get to a host, and the host will work out what application needs this data. So look at the port numbers and pass it on to your web browser, or whatever it may be, so it's used by the user. So as it says here, so it's a process of building up our packets, encapsulation, transmitting them, and then removing those headers and extracting their message so we can pass it up to the applications on our machines. Okay, just for the moment, we'll step back in time. So where did the internet come from? So back in the day, in the 1960s, the US Department of Defense, they wanted to create a resilient network, something that would survive a nuclear bomb. So if part of the network went down, it could reconfigure itself so you could still communicate to all your military bases across America. So back in the early days, the internet, or the ARPANET as it was called back then, could be drawn on a single side of A4, as we can see in this diagram here. So the research work that went into the development of ARPANET was done by US universities. So at the beginning, they were looking into different ways of how you could build these types of packet switch networks. So they were looking at different protocols. But then over time, they settled down onto TCP/IP, which we still use today. So in this diagram here, the ovals are different networks. So just like the internet, ARPANET was a network of networks. So each one of these ovals is a separate network connected via a router together, so they form a bigger network. So to identify the different networks and the hosts, the computers on that network, you need an address, you need an IP address. And back then, and it's still used today, is your Internet Protocol, or IP. More specifically, IP version 4, which identifies the networks and the hosts using a 32-bit number. So those 32 bits are broken down into 8-bit chunks, and each 8-bit chunk is represented by a decimal value. So you can see, for example, here you've got 10, 2, 0, 5. So the 10 is 8 bits, the 2 is 8 bits, the 0 is 8 bits, and the 5 will be 8 bits. So that's a 32-bit number represented in what we call a dot decimal format. So back then, each of these major networks was identified by the first digit. So you can see ARPANET, the first decimal digit is a 10. The Stanford Research Institute started with a 2. So all addresses within this network start with 2 dot something or other. So that meant you had 24 bits to represent your other networks, your other sub-networks or machines on that network. So that allowed you to have approximately 2 to the 24, 16 million different addresses within that network. So each machine within these networks of networks was given an IP address, and knowing that address, one machine could talk to the other. So machines in this network would send out the address they want to talk to. Maybe it was an address in the ARPANET starting with 10. So it would go to this router here, and this router would then know where to send that data based on that IP address, and it would send it obviously here. And within this network, it would then finally get routed to the destination machine. Now, back then when they were designing IP version 4, obviously someone made the choice going, we'll never need more than 2 to the 32 IP addresses. And as you probably guessed, yes, we do. So we ran out of IP addresses years ago. So to handle that problem, we moved over to IP version 6. And now, rather than using a 32-bit address, we use a 128-bit address, which gives you obviously a lot more addresses to use. However, as most of the machines out there still use IP version 4, a 32-bit address, This will be the protocol we'll be focusing on when we're looking at our network layer. Obviously, over time, the internet grew and grew and grew, and in the 80s, the US Department of Defense passed over control to government departments, industry and academic partners. Initially, quite a few of these were over in America, so like NASA, for example, and the US universities that had been involved in the original development of ARPANET. But over time, obviously the rest of the world joined in, and from a UK university point of view, that's when we saw the development of JANET, so the Joint Academic Network. And that was a network that connected together universities in the UK, and it started to become the norm around about mid-80s. So if you would like some more information about JANET, obviously there's a webpage for that, and nowadays moved over to Super JANET. Obviously, over time, the backbone network that connects all the universities together across the UK has been ever improved, giving ever faster and faster network speeds. So as we know, the internet is a network of networks, and it can be divided down into a series of tiers. So your tier 1 networks are your high-speed global interconnection networks, and these tend to be maintained by your big players in the communication market. So AT&T, Amazon, Google, T-Mobile, Orange, you name it, your large telecommunication companies. And they provide the backbone of the internet. And generally speaking, they share this resource, so it's a settlement-free connections for them. So it's a bit of a gentleman's agreement. So you can use my network if I can use your network to route the traffic around the world where they need to get it to. Obviously, as we go down these tiers to tier 2 and tier 3, you start to pay for your connections. You start to pay for the number of bits per second you want in your communication links. So connecting our tier 1s to tier 2, we have internet exchange points, regional exchanges. And if you'd like a little bit more information about those, these are companies that specialise in connecting networks together, and some links down the bottom here where that's discussed in a little bit more detail. So as we move down into tier 2, we start to get our regional ISPs, so BT for example, and finally get down to tier 3, your home connections, your home internet service providers. Now, typically how the tier 1 networking is constructed is a bit of a secret, or if the big companies don't advertise where their tier 1 lines are from a security point of view. But what you can see is a graphical representation of where these lines cross the ocean, and it's a nice website here to go and have a look at. So if you go to this webpage, you can start to have a look at all the different cables that are crossing the various oceans to connect the world together. So if you think back to where we had the TAT1 cable, they were coming out of Cornwall Ways, going across to America, and you can still see there's a density there. Fibre optic cables taking the kind of same paths across the ocean. So if you click on these cables, you will be told the name of the cable, the company that owns it, and its length. And when you look at the cable suppliers, you can see here, sometimes it's a bit difficult to find out who actually owns it because they're all sub-companies of bigger companies. One I did manage to kind of look at was a new one from America all the way across to Singapore. And that's the Bifrost, because the name stood out. The Bifrost cables, because obviously the name stood out from too much watching Marvel films. So that cable is around about 20,000 kilometres, connecting America all the way across to Singapore. You can see here, these are the owners, and I believe some of them are sub-companies of Amazon. And when you look online, I think the estimated cost is around about $800 million. So you can see now in tier 1 networking why companies kind of share cabling. So it's difficult for any one company to have cables that cover the whole world and have cables that allow them to have the bandwidth that they need across those links. So sharing these costs obviously makes sense for these big companies. So I think these cables here are designed to carry 10 terabits per second across the ocean, which is obviously a reasonable piece of bandwidth. So that was just a quick overview of what the internet is. Basically a network of networks, a global network that allows you to connect machines across the planet. So when you make these connections, we typically use a client-server model. So your machine will be acting as a client requesting services from a server. So for example, the server could be a web server. So it's a machine waiting for web connections. So as we saw previously, machines are identified by their IP address at that 32-bit number. So that uniquely identifies them on the network. So your client will access the network via the application layer. It will construct a message that will be sent down our protocol stack, and then transmitted across the internet. It'll be routed to the right place. We'll look at how it does that later on. Received by the server. The server will receive that message, receive that request, and then send out a response that will be received by the client. So the software object your application connects to is called a socket, and that socket is used to identify the piece of software running on the server that you want to connect to. So as you probably can imagine, each server could be running multiple network services. So it could be running a mail server, a web server, different stuff. So obviously you need more than just the IP address to identify what you want to connect to. So the IP address will identify which machine you want to connect to, but to identify what service you want to connect to, which program process running on the server that you want to connect to, that's done by a port number. And you define that when you make your connection to that socket. I want to connect to port 80, if it was HTTP, a web page. That particular web server, the actual software, the process running on that physical hardware, the server. Too many servers, but hopefully that makes sense. And we'll be looking at these in more detail as we go through the module. But the key thing to identify here is you have a client and you have a server. They're both identified by their IP address. The client will connect to the server using a socket, and each socket is assigned a port number. And as you can imagine, this needs to be agreed upon by the people who are writing the software. So as always, there's a web page listing these. So if you go to this web page, you can see a list of standard port numbers. So if we go down here and look, there we go. Port 80 is for HTTP protocol. So on the server, you'll have a piece of software listening on port 80 for incoming requests from people that want to access your web pages, etc. Obviously, on the same machine, you might have an email server, and I'll be listening on port 25. So here we go. So that's where your email server will be listening for incoming emails. As I say, we'll be looking at more of these in more detail as we go through our protocol stack, but just to introduce the basics. So to show all this in action, we have some demos in the lecture review session. So we'll be looking at how long it takes for our network packets to get to different parts of the world. So we'll be pinging things. We'll have a quick discussion of how those domain names get resolved into IP addresses. But again, as always, we'll be going in a lot more detail about that one when we look at DNS. We'll see how we can identify our network interfaces on our Raspberry Pis and identify their IP addresses and use traceroute to show the path taken by our packets as they cross that network. And start to analyze all these different numbers and what do they mean. Okay, our first protocol, so HTTP, so Hypertext Transfer Protocol, not to be confused with HTML. So HTML is the markup language that is used to define what your web page looks like, and HTTP is the protocol used to transfer those web objects across the internet. So a mechanism to allow you to request the web page, the HTML, or its embedded objects, such as images or whatever other things nowadays you've got embedded in that web page. So as we were saying, this runs a client-server model. So your web server will be listening on port 80 for incoming connections that are using the Hypertext Transfer Protocol. Now, over the years, HTTP has gone through different flavors. So to start off, we'll be looking at the basic one. So HTTP version 1.1. Obviously, as the internet increased in size and people started to use web pages for different functionality, security became an issue. And also speed, the amount of time it takes to transfer these web page objects using HTTP. So different optimizations have been made to increase performance and improve security. So just to introduce some terminology, so HTTP uses TCP links. So what that means is that's a reliable connection. And those connections can either be persistent or non-persistent. So if they're non-persistent, you request the object, and then that link is closed. And then if you want another object, you have to reopen a new link to the server to transfer the next object. And obviously, opening and closing communication links takes time. So it's more typical nowadays to have persistent connections where you can transfer multiple web page objects across the same link. So you're not constantly bringing up and down those connections. And obviously, that improves performance. You may therefore ask, why didn't they do it from the beginning? Why do we have non-persistent links? Well, obviously managing those sessions that transfer multiple objects is a lot more difficult. It's far simpler just to create a new connection for every object. So again, a bit of a trade-off. So HTTP is a stateless protocol, so no information about previous connections are maintained on the server, which has the advantage, obviously, it reduces the server's load. It reduces the amount of data the server needs to maintain. Obviously, there's some disadvantage taking that approach, not remembering what has been done previously. So to get around that one, cookies were invented, a way of logging your movements through the web page. So we don't look at these in this module, but something for you to look at in your own time. So the question arises, what is a protocol? But basically it just defines how two things talk to each other. So what language you'll be using, what functionality you'll provide. So you'll be defining request and response messages. So you have to define the syntax of those messages. And HTTP is a nice one to start off with. Because it's one of your older protocols, everything is sent in plain text. Obviously, the later versions of HTTP start to encrypt stuff, but HTTP version 1.1 is just sending plain text, which you can read. That you can read on a terminal, that you can see as the communication process unfolds. And we'll be doing that in the lab. We'll be using Telnet to actually type out our HTTP requests to the server and display the responses. So from the client end, you need to send your request to the server, and it will be constructed in this format. So as I say, plain text characters. So the first thing you will send is the method. What do I want to do? Do I want to get a web object or send you some information? Or am I looking to see what the server will support? So the options one here. Obviously, back in the day when HTML was first created, the intentions were that HTTP would allow you to read and edit documents online. So some of these methods are a little bit dangerous and have been removed now. So the ability to delete a web page, for example, useful, but perhaps a little dangerous. So not many web servers will support that now. So that's where you can request the options of which of these methods does the server support. Then we have a space character, then the URL that we want to access. So which web page do I want to access? Another space. Then we tell the server what version we'll be using. So we'll be using HTTP version 1.1. And then to show to the server that that's the end of that line, we have a carriage return. So a carriage return line feed. That's how the server breaks up the message into its various chunks. So we're using the carriage return line feed characters, 0A, 0D, hexadecimal, to indicate the end of our line. Then we have one or more, typically a few, header fields that describe what language do I want to use, which particular web server am I accessing, what media types will I accept, and they're all defined here. And again, each one is indicated by its name, space, and then a value, and again terminated with a line feed carriage return. Obviously nowadays web pages contain a lot of different things, not just text and images. So these are defined and encoded using the multipurpose internet mail extensions. And we'll see those in the lab again as we go through. Finally, when you've finished specifying all the additional information that you're passing to the web server, you show that you've finished by a carriage return line feed on its own, a blank line. And if you need to, you can send additional text. So if you're using the post command, if you're sending your name, for example, through a web page to a web server, that would appear in the body here, down the bottom here. Okay, the web server will receive that one, work out whether that's for them, and then if it is, it'll start processing it, and it'll start to generate the response packet, the response message. So again, we're breaking it down into lines, and the end of each line is indicated by that carriage return line feed. So the server will return back the version of HTTP it's using, its space, any status codes. And we'll look at those in 2 ticks, but you've probably seen those already, 200, 400, probably ring a bell. Did your connection go through or was it rejected? So you have a number, a status code, and you'll see they're in the family of the 100s, the 200s, 300s, 400s and 500s families. We'll see those in 2 ticks. And then you get a human readable phrase. It was okay, a bad request, not found. That represents that number. So as I say, in the early days, you had readable protocols. You could see what was going on. The protocols used plain text to communicate. And again, you'll get a load of header fields with additional information. So the header field, space, and a value, terminated by our carriage return line feed. Again, to indicate that you've finished sending that additional information, you have a blank line, and then you have your body of your response, which will contain, if you've requested, for example, a web page, some HTML, some text characters, or an image, so encoded using those previous extensions we talked about, which will obviously contain your images or your videos, your music, whatever it may be that you have requested. So, key thing to latch on to here is the protocol defines how the client and the server will talk to each other. What language will they use? What words will they use? And in HTTP, they are actually words that are human readable. So when you're typing these out on the keyboard via Telnet, you can't just use any characters because those are not defined in the protocol. So for example, if you're typing out the string get / the top web page, HTTP /1.1 carriage return, you can't use a delete key, can't use cursor keys because the web server doesn't understand those characters. So with a protocol, you're defining everything. What I will send as a client to you as a server and what you as a server will send to me. That all needs to be defined. And if you go outside of that definition, it won't work and you'll get some of these. You'll start to get error codes. If you see something in the 400s or something in the 500s, that's either a client error or a server error. So 400, for example, when you request a web page which is not there, a bad request. Hopefully everything works fine, so you'll see the 200s. So if you get a 200, that's good, everything is okay. And you get general information commands as well, which will be the 100s. So as you could probably imagine, there's a lot of error and status codes. So as always, if you would like some more information on that, there's a web page for that. So if you go to this web page here, you can start to look at all the different error and status codes. And there's one or two. So I'm not going to go through all of these, but you can have a flick in your own time to see if you can see any ones that you've seen before. So demo time. So in the lecture review session, we'll go through that one and see it in action. So we'll have a look at what you'll be doing in the lab. So as I say, we'll be using Telnet to directly talk via the keyboard to the web server. So you can request your HTML or images directly by typing out a sequence of characters. That is the protocol. We'll be typing out the protocol commands directly using Telnet. Obviously that's a very painful way of doing it, but you get to see everything there, so that's why we're going to be doing that one. The far easier way of doing it is to obviously use a client, your web client, your browser. So each Raspberry Pi has a web server, and on there you can pass some data and it will pass back a response. So here we have a web page. We'll be running on the Raspberry Pi. We can click the submit button, which will send a post command, which will transfer your name over to the server, and then the server will integrate that into its response and say hello. As I say, we'll go through this in more detail, but so Telnet is just a way of sending ASCII characters across a network connection. So normally you'd be connecting to port 23 and you'd be opening up a terminal on a remote machine, so allowing you to execute commands, etc. But you can also just redirect that to a different port. So if you were to open up a Telnet session to your web server's IP address and connect to port 80 rather than 23, you'd be sending characters to the web server. So you can just type out your HTTP requests, and that's what we'll be doing. So as I say, in this module, we're going to start at the top and work our way down our protocol stack. The advantage is that obviously we can ignore for the moment some of the lower level details, but even still, some of that sort of creeps in. We've already had to sort of talk about IP addresses, etc. But there's a lot more detail that we're ignoring for the moment, but we will look at it as we go down our protocol stack. Generally speaking, each layer is separated from the one above and below it. So you don't want to repeat data or repeat operations within the same layer. But there's some leakage between layers, and we'll see that as we go through. But each layer should do one thing, and it should do that one thing well. Your typical OO design techniques. So do stop and think about what a protocol is. So do look at the HTTP protocol. Again, we'll be looking at that in a lot more detail in the labs. We'll be capturing HTTP communications using Wireshark, so you can see what's actually being transferred between the client and server, because you can capture those packets. And not to give the game away, you'll be writing some code to request HTTP objects in Python. So you have to understand the protocol, what language the client and the server are speaking. Okay, to reinforce those points, the concept of what a protocol is, we're going to look at another protocol in the lab. So we're just going to touch upon it in the lecture here. So FTP, so our file transfer protocol. And I guess technically this protocol predates the internet, dating back to the 1970s. Obviously, one of your key functionalities of any network is to transfer files. So you need a protocol that will transfer your files across the network, and that was FTP. Nowadays it's less commonly used owing to security issues. So again, like the early versions of HTTP, usernames and passwords and data are sent using plain text, so there's no encryption. Now, that may sound like a significant disadvantage, and for some things, yes, obviously it is. But if you're just transferring standard stuff across the network, so you're downloading an ISO image of your latest flavor of Linux, obviously that doesn't need to be encrypted. So it still does have its place. But if you're transferring more sensitive files, then obviously there are encrypted versions of these. So secure FTP comes in different flavors. They seem to have a random placement of the S. the one I typically use is SFTP, so secure FTP. It normally comes wrapped up with SSH when you install it on your machine. So a good thing about FTP from a teaching point of view is it's slightly different to HTTP in the sense that we have two channels now. We have a control channel which we send our commands across, and we have a data channel. And to identify those two communication links, they're given different ports. So when your FTP client is connecting to the FTP server, you'll connect to port 21 to send your commands to put and receive files, for example. And your control channel is persistent. It's a stateful connection. The server will maintain information about who you are and where you are in the file structure, for example. However, your data communications are done across a separate channel. They're out-of-band communication. So every time you want to transfer a file or some data, that is a separate connection. So a separate connection will be established. And depending on the mode you're using, passive or active, that could be on port 20. So the server would connect to port 20 on the client to do those transfers. Particularly, we don't use active mode nowadays because of firewall issues. We tend to use passive mode. And the port values will be assigned from a specific pool of values that are available to us. We'll look into that later in the lab when we use this protocol. Again, just like HTTP, we want a reliable communication link, so we use TCP. But as I say, the key thing to identify here is you have two separate channels. You have two separate communication links. You have one for control, one where you send your commands, and one for receiving or transmitting data. In the lecture review session, we'll do some demos with the actual Raspberry Pi systems. But as you can see here, it's a very similar format to HTTP. So these are our commands, so we can specify the username, the password, whether we want to store or retrieve files. These are our commands, and again you get very similar status codes coming back, whether it worked or didn't work. And again, just like HTTP, we can send these commands, these request messages, using Telnet, so we can connect to port 21 on the server and issue these commands. But again, to say the key difference here is that we need two communication links. So you can see I've got two terminals here. One for the command and one for the data. So if I issue a list command, I want to see a directory listing, that will not be displayed on this terminal in this communication link. You have to set up a separate one where you'll get the directory listing coming across, because that's your data. We will also obviously be capturing all of this in Wireshark, so we can see all these packets. We can see that interaction between the client and server by looking at the flow of packets between the client and the server. Again, to simplify this process, rather than sending these commands directly via our Telnet terminal, we can use an FTP client, which simplifies these commands, or a graphical GUI interface, make it more drag and drop. And we'll be looking at all of those in the lab. As in addition to looking at this protocol from a protocol point of view, we'll also be using this to transfer our files onto and off the Raspberry Pi system, so between the PC and our test systems. As always, if you would like a little bit more information about these commands and the status codes, etc., there's a web page for that. So if you want to follow those web pages here, you can see the full set of commands and the full set of status and error codes. Fingers crossed, touch wood, you won't have too many error codes. So as I say, we'll be looking at this protocol in more detail in upcoming labs. So I think lab 4 from memory. So you've got a little bit of time if you want to have a little read around about what this protocol does do. And I definitely recommend having a skim through the RFCs for each of the protocols. Maybe not analyse them in minute details, but have a quick flick through. It gives you a flavour of what's going on with these protocols, what problems they're solving for their intended application domain. Okay, so the final protocol for this set of lectures, we're going to look at SMTP, so your mail transport protocol. And again, here we have its RFC, so 5321, have a look at that one, see what that protocol defines. So this protocol, again, dates back quite a long way. It dates back to the 80s. But as I said in lecture 1, you can trace back the internet's expansion because of this protocol, because of emails. So again, we have our client-server model. So we connect to the mail server using this protocol. So this is a push protocol. So you don't read your emails using SMTP. You use SMTP to transmit your emails to the destination email server. So SMTP is classified as an end-to-end model. So rather than trying to solve all the problems of retransmission and error detection in the protocol, some of this is passed over to the mail servers. So you'll connect to that mail server, and then it will then relay that on to the next email server. And if it can't, then you'll get that bounce message coming back at the end. So the default port for SMTP is port 25, so exactly the same as HTTP and FTP. We can use our Telnet instruction to connect to that port and interact with the mail server. So this will be, again, a reliable connection, so we'll be using TCP, and it's a persistent connection. As obviously like FTP, you'll need to log into an account with a username and a password to allow you to send that email. Again, SMTP is a plain text protocol, so it's a human readable protocol. And originally the RFC defined that the main body of text should use 7-bit ASCII encoding, which does add a little bit of complexity. So again, we use multipurpose internet mail exchange format to encode different files into this format. So if you go back to sys1, you can think about it as that PPM image format. So there we encoded our RGB values as plain text within that file, if you remember. So as I say, SMTP is a push protocol, so you can't use it to read your emails. So back in the old days, you had to Telnet into the email server itself, so you could access the raw files, you could read the emails that way using an email client there. But if you want to pull off the emails from the email server, if you want to retrieve them onto your local machine, onto your PC at home, we have to use another protocol, either POP or IMAP, so Post Office Protocol or Internet Message Access Protocol. And again, we'll be looking at those in the lab in more detail. So in Lab 2, we'll be looking at HTTP and SMTP. So what I would like you to do is a little bit of research. So I'd like you to go out and read that RFC, so RFC 5321, and do a little bit of investigation about how SMT works. So how do you send an email? How does your email client connect to someone else's mailbox? What series of steps do you have to go through to push that email message across the internet? So yeah, a little bit of homework there. So do have a read around for Lab 2. Okay, so finish up. So a bit of a summary. So obviously the main purpose of a network is to connect machines together. And if you're connecting machines together, what do you want to do? Well, you want to transfer files. So if you want to transfer files between the two machines, you'll need a protocol. And there's different ways of doing it. In this lecture here, we've looked at HTTP, FTP, and SMTP. So we're looking at different ways of transferring files, information, data between our various machines on that network. So we saw to identify the machine on the network, it needs an IP address, that 32-bit number. Then to identify which service we're connecting to, which software server we're connecting to, we need to use sockets and port numbers. So port numbers 0 to 1023 are defined as system ports, standard ports, and they've been assigned to core protocols. 1024 up to a big number, 49,000 odd register ports. These are considered application-specific ports. And those are assigned by IANA, the Internet Assigned Number Authority, if my memory serves me right. Basically a non-profit company who is in charge of managing the internet. Then we have ports 49,000 up to 64K are called ephemeral ports. These are obviously when you make a connection between two machines, you have a destination port that you want to connect to, but the receiving end on the client also needs to have a port number, and that will be assigned a port number from this pool. So these are short-lived ones. The exact range depends on the OS, but for each connection you need a port number on the client and you need a port number on the server. And as I say, we'll be going into a lot more detail on that in the actual labs. You'll see that in action. So hopefully that gives you a quick intro into what we will be doing in the upcoming labs. But we have some unanswered questions. And as I touched upon at the start of this lecture, we'll be looking at some of the more housekeeping protocols to come in the application layer. So protocols that will assign your machine an IP address. So when it connects to the network, what IP address will it be given? And also we need protocols that will map our domain names, our URLs into IP addresses. And we also need to keep one eye on what's happening lower down in that protocol stack. And that's all to come in the next lecture. So I think I'll leave it there for now, and I'll see you next time.